Guys, welcome back to TechDose, and in this video we will look at maximum number of points from grid queries problem, which is from Leetcode number 2503. Let's now read the problem statement. You are given an m by n integer matrix grid and an array queries of size k. Find an array answer of size k such that for each integer queries at I, you start in the top left cell of the matrix and repeat the following process. If queries at I is strictly greater than the value of the current cell that you are in, then you get 1 point if it is your first time visiting this cell, and you can move to any of the adjacent cell in any of the four directions: up, down, left or right. Okay, now otherwise if the first case is not true, then you do not get any points and you end this process. After the process, answer at I is the maximum number of points you can get. Note that for each query you are allowed to visit the same cell multiple times. That means reusing the cell for each of the query is allowed. Return the resulting array answer. Now let's look at the given example here. If you see this 3 by 3 matrix, then the grid is already given. The queries are 5, 6, 2. Now if you try to find out, if I have to start in the top left corner, then how many maximum points I can cover if all the four directional movements are allowed. So in this case, the first query is having the value 5. That means if you start from the first cell, you can cover all the adjacent cell in all the four directions if the value is strictly less than 5. So how many such cells can you cover? You can cover 1, 2, 3, and you can cover 2 and 3, but you cannot move to this 5 because the question mentions about strictly increasing value, but 5 is equal. So you cannot move here. Okay, these values cannot be done. So you have covered these 5 cells, right? Definitely the out of bound calls will not happen. Therefore, for the first query, the answer will be 5. Now how to calculate this? Well, you can apply either the depth first search traversal by using recursion, or you can apply BFS by using Q. So I will be preferring this BFS because it is easier to debug as well. So for 5, you can calculate the value will be 5. Separately, you can calculate for 6. So for 6, what you will do is, again you will start at this point, okay, and you will be trying to traverse to all the points. So can you traverse all these points again? Yes, definitely, because whatever points you can traverse using 5, definitely with a higher value you can at least traverse those points, and you may be able to traverse more. So in this case, you can traverse this 5, 5, 1 as well extra. You cannot cover this 7, but you can cover 5, 5, 7, this 5, 5, 1, right? So whenever the query value is higher, it will always be able to cover all the points that the smaller value can cover, because the starting position is same. The starting position is always the top left corner, right? So 6 will have at least 5 count plus 3, which is 8 in this case. Now if you talk about 2, then maybe it will be starting in the beginning and it will not be able to cover anything, so the count will be 1. Maybe the first cell was having value, let's say 5, and the query was about the value 4. So if you start at the top left corner, then you will be covering 0 cells because you cannot cover even the starting cell in this case, right? So that can be considered as a special case. You cannot even get started, even though other values are maybe smaller which are lying adjacent, but even at the start point the value is higher, so this query 4 cannot even get started. Now if you follow this technique of solving each of the query by traversing through the matrix again and again, then you can imagine that it is an m by n matrix. So for each of the query you may have to traverse m by n times, and so in the worst case you will be taking query number of times m cross n, right? Now let's see if this time complexity is feasible. So if you look at the constraint, then m into n value is 10 to the power of 5, and how many queries are there? The queries are maximum 10 to the power of 4. Okay, so in the worst case you will end up doing 10 to the power 9 operations, and you know that it is greater than 10 to the power of 8, which is our standard for 1 second. So this will give you TLE for sure. Okay, so we will not be following this. Now let's look at some observations which will help us solve this problem optimally. Now if you take an example here, which is a 3 by 3 matrix, and let's say that we have certain queries 5, 8, 2, 5, 4. Now I already told you that if you are finding the query for, let's say 4, you are solving the query for 4, what all nodes can you cover? With 4 you can cover these 3 nodes. because you are starting at the top left corner, you can cover these 3 nodes. And if I ask you about what all nodes can you cover with 5, then definitely with 5 you can cover all the nodes that you can cover with 4, and maybe you will be trying to cover something extra as well. So yes, with 5 you can cover this 4 and this 4 as well, so 2 extra coverage, right? You cannot cover this 866 because the value is 5. So what happens is, you can try to solve this problem incrementally, because why did our time complexity actually exceeded the expected time? Because we were traversing through the matrix again and again for each query. So what we have to do is, we have to devise a technique in such a way that all the queries can be solved by traversing through the matrix exactly one time. Exactly one time, okay? No more than one time. So don't you think that if I just solve these queries in random order, it will not be achievable? Instead of doing that, what I have to do is, I will be sorting this entire set of queries. So we have 5, 8, 2, 5, 4. So I can just sort it as 2, 4, 5, 5, 8. So these will be the queries. Why I have sorted it? Because you know that if I have covered, using this 2, if I have covered just one node here, then I can just remember what all nodes I will be processing next. That means all the adjacent node, I can just save all the adjacent node 3 and 3. And when it comes to 4, I can start processing from there and add the previous counter. So how many nodes actually 2 had covered? One node. So I can add 1 to the extra nodes that 4 can cover. So can 4 cover this 3 and 3? Yes, it can cover. So 2 extra nodes it will be able to cover, but it will not be able to cover these 2 4s, right? So the total coverage for this 4 is 3. Now when you are solving for 5, then what we will do is, we will be actually saving all the nodes that actually 4 could not cover and was adjacent to what it could have covered, right? So it covered 3 and 3, and the adjacent nodes which the 4 could not cover is this 4, this 6 and this 4, right? So this will be saved somewhere. So if I have saved this and now I am solving for 5, I will be getting the answer for this 4, which is 3, and to this I will be adding the new nodes that 5 can cover. So what 5 can cover is, it can cover this 4, 1 extra, 2 extra, but it cannot cover this 8, 6. So this 5 could cover 2 extra nodes, and so the total coverage became 5. Okay. And what all nodes are adjacent and this 5 could not cover? 6, 8, 6. 3 nodes, right? Now when it comes to this 5, since these values are duplicate, therefore the count will exactly be the same and I don't need to solve. Okay. So why not remove the duplicates? Why not remove the duplicates, and later while returning the answer I can just copy this result multiple times, as many times as the duplicates are present. Okay. So I will not be taking the duplicates while processing. So I will be maintaining sorted queries set. Okay. Now when it comes to 8, then get the count from the previous query, which is 5. So the count was 5, and to this try to process all these nodes which we are currently seeing, 6, 6 and 8. So what all can this cover? It can cover the 6, 6, and it can also cover this 2. So 3 extra nodes can be covered. So it will cover 8 different nodes, right? It will cover 8 different nodes, but it cannot cover this 8, and that is completely fine. So we are done processing, and you see how incrementally solving will actually lead us to parsing this entire matrix exactly one time, and that can only happen if we are solving the queries incrementally using the sorted queries set, which will avoid the duplicate queries, as well as help us in incrementally solving and utilizing this idea which we have seen, right? Now if you think about implementing this idea, like we have known the idea. Let's say that if you were solving for this 4, okay, if you were solving for this 4, then you had solved this 2, 3, 3, but the next nodes which you could not solve was 4, 6 and 4. So you have to remember, right? You have to remember it somehow. One way to remember it is by using a queue. So by using the queue, you remember the next level of nodes that you could not actually solve. Okay, that you could not actually solve. And when the new query comes in, let's say the new query comes in for 5, then the 5 will actually be checking with all these nodes one by one if it can solve it. So if it can solve 4, then that is good. It will be removed from the queue and 8 will be pushed into the queue. If it can solve this 6, I mean it cannot solve this 6, so it will be skipping it. If it can solve this 4, then yes, it will be removed from the queue and the next node will be pushed. So this is one way, and this is not a very good way to do, but yes, it will also pass. You can try this out. But the best way to solve this would be to greedily pick the best option as the next best option, you can say, right? So if I have solved for 4, then for 5, out of these options 4, 6 and 4, which will be the next best option for this 5? It will be 4, because the smallest of the next to be solved will be the next best option. Because if I say that this was, let's say, 60, this was 40, and this was, let's say, 34, then if I was solving for 5, then the best option is 34, because it is smallest of all the pushed items. Now if this 5 cannot solve for the smallest item, then I don't have to go through all the items and check if it can solve for 60, if it can solve for 40 or not, right? If you cannot beat the weakest guy, then you cannot beat anyone in the group. That is the idea here, okay? So I will always go with the best next pick, which can be implemented by using a min heap in this case, because I am trying to figure out what is the next option which is the smallest in value, so that it can be actually covered by the current query. So I think you got the idea, and in this particular case I will be going with BFS, because this makes sense in covering the entire matrix by using the 4 directional traversal. Okay, so I think the observations are pretty clear, and you might now be knowing about why we are using BFS plus min heap in this case. So this will look a lot like Dijkstra. In this case we are not trying to find the shortest path, but the Dijkstra algorithm is a greedy approach to reaching from a source node to a destination node, you can say, right? So in this case we are trying to utilize the greedy algorithm, which is Dijkstra, starting from the top left corner and trying to cover the entire matrix cells as much as we can, right? So we are applying the greedy algorithm, which is very similar to your Dijkstra, but the difference is in this case we are not finding the shortest path. Okay, let's say that we are given the grid, fine, and we are given the queries. So from these queries, first of all I will be forming the sorted query set. So I have formed the sorted query set, which is 2 4 5 8. So all the duplicates are gone and the values are incrementally present now. I will be taking a counter which will be counting about how many nodes have been solved for a query, and it will remember the count for all the past queries, so that the new queries can actually add up those values simply, right? Then I will be using a map. So I can take a map using a KV pair, where the query will be the key and the count will be the value. This map will actually help us to remember for each of the query what were the values, because maybe you will be having repeated queries and maybe the order in the original queries was different. So in the answer you have to return the order of answer as same which is given in the queries, right? Not in the sorted order. Fine. So for that reason I have to remember each of the queries answer, and that has to be done with the map. So I'll be taking a hash map here. We will be applying the BFS algorithm, and I will be taking a min heap where each of the node value will be the value at the grid and the XY coordinate, which is the row comma column. Okay. Now initially, since I know that I will be starting at 0 comma 0, so I will be pushing this node 0 comma 0 with value 2 into the min heap already, and I will be marking the visited array with true. The visited array will make sure that you do not reprocess the cell again. Okay. Now let's start the processing. So we will start the processing with first query, which is 2. This 200 will be taken out. So our current node is 200. You compare this 2 with the given query, which is 2. Yes. And now since this 2 is actually not less than the given query, therefore you will push it back into the heap so that it is not lost, and we will move forward. Like this query is done. Okay. So whatever is the count you have to save for this query 2, the answer will be 0. That means the query 2 could not cover any cell, and as you see, you cannot even cover the starting cell as well, right? Now let's go to the next query, which is 4. Now again you remove the top of the heap, so it will be 200. Check out this value 2 with 4. Is this 2 smaller than 4? Yes, it is smaller. So increment the count that you can cover this cell, and when you can cover this cell, then you will try to make all the 4 directional calls. So if you try to make the top or the left call, they are out of bound. If you try to make the right call, this is value 3. So you can push this into the heap 3, which is having coordinate 0 comma 1, and mark this as true, which is visited, and you can move this 3 as well, 3 at 1 comma 0 coordinate, and mark this as true as well, right? So this 200 has been processed. Now the next best option will be taken out, and these two 3's are same, but the second value of this 0 is smaller, so this will be taken out. 301. Now in this case, again check this 3 with 4. 3 is smaller, yes, so increment the count to 2. Okay, so this node has also been covered by 4. Now check out, you cannot make the top call. Can you make the right call? Yes. So you push this 4 comma 0 comma 2 and mark this as visited. Can you make the down call? Yes, you can make it because it is valid and also it is not visited, right? You can make it as true and mark push 6 comma 1 as well. Okay, can we make the left call? It is not possible because this is already visited. Fine, we are done with 300. Now let's pick the next option, which is 310. So 310 is taken out, and in this case again 3 is less than the 4 value, so we will increment the count. So we have covered 3 nodes now, 1 node, 2 node, and 3rd node. Okay, now you just find out all the 4 directional calls. So in top it is already visited, on the right this has also been visited, down this is not visited, so you can push this 4 with the coordinate 2 comma 0, and on the left hand side this is out of bound. Okay, so we are done with 310. Now let's pick the next best option, which is 402. So 402 is taken out. Now you compare this 4 with this 4, so they are the same, so that means this cannot be covered by 4. So what you do is you will push it back, into the heap. So 402 will again go back into the heap, and for this query 4, how many nodes we could cover? 3 nodes. So 4 will cover 3 nodes, and that is what is saved in our map. Okay, so at this point of time we have this 4, 6 and 4 present in our heap. Okay, so what is the next best option for the next query 5? So for the next query 5, the next best option will be 402. So 402 is taken out. Okay, compare it with 5. So 4 is smaller, so this is covered. 402 has been now covered. Increment the count to 4 and try to make the 4 directional call. Well, the top right calls are actually invalid. The down call is 812, so you can insert 812. Okay, fine, and you can mark it as visited. Now when we had actually visited this, we should have marked it as visited as well, right? So you can mark it as visited, 812. We are done, and to the left hand side it is already visited, so no need to make this call, and we are done with this. Now the next best option is 420. So 420 is taken out. Okay, again compare this 4 and 5, and this 4 is smaller, so increment the count to 5. So this has been covered as well, and from here make the top call. It is already covered. The down and the left call are actually invalid, only the right call can be covered. Okay, so we will be pushing 6 comma 2 comma 1, and you can mark this as true as well. Okay, now the next best option will be taken out, and you check it out. 611, 812, 621. So 611 will be taken out. So if 611 gets taken out and you compare this 6 with this 5, so 6 is actually not less than 5, so we will be pushing it back into the heap. Okay, because it cannot be covered by 5, so whatever is the count, you just save it. So 5 can actually cover 5 nodes. Okay, and we have saved it. Right, now we will be going to the next query, which is 8. Now let's pick out the next best option. What we are looking at? We are looking at this 6, 6 and 8. So the next best option is 611, that is taken out. 611. Can we cover this using 8? Yes, 8 is larger than this 6. So increment the count and make the 4 directional call from this 611. But you will find that all these nodes are actually visited, all the 4 directions, so nothing will get inserted, and we are done. Now the next option will be 621. So take out this 621. Okay, now compare this 6 with this 8, and actually 6 is less than 8, so increment the count to 7. This has been processed, and from 6 to 1 you try all the 4 directional calls. The top and the left call are actually visited. The down call is invalid, only the right call will work. So mark it as true, that means visited, and insert the node which will be 2 comma 2 comma 2. Okay, so that has been inserted and this is done. Now the next best option will be triple 2. So triple 2 is taken out. Compare this 2 with 8. 2 is smaller, so increment the count to 8 and try to make all the 4 directional call. So this right and down call are actually invalid. The top and left call have already been visited, so nothing will get added and we are done with this triple 2. Now the next option is 812. Take out 812, and if you compare 812 with this 8, 8 is actually not less than 8, so you will push it back into the heap and we are done processing for this 8. What is the count for 8? The count is 8, so you save it. Okay, and we will be going to the next query. So there is no next query, right? And we are done, and we have processed all the queries and have been saved in our map. Now what is the next step? Next step is to build the result. So I will take a result array and simply it will be of the size of the query. So when I go to this 5, I can look up from the table and say that okay, 5 number of cells can be covered with the query 5. You can look up 8 number of cells can be covered with the query 8. You can go to 2 and say that 0 number of cells will be covered with the query 2. You can go to 5 and say that 5 number of cells will be covered with the query 5, and with 4, 3 number of cells can be covered with the value 4, right? So this is how you can build the result, and this is your final answer. So I hope this is clear. Now in this case, we are using extra space, which is the visited array and the heap. So you can consider the extra space to be mn, order of mn. And you know that in heap the push and pop operations are log of size of heap. So let's consider that all the elements can be into the heap. So you can say log of mn for each of the heap operation, and we will be doing mn number of operations. Therefore the time complexity will be order of mn log mn, and the space complexity will be order of mn. I hope this entire approach is clear. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this problem, we are given the grid and the queries. So first we will be taking an ordered sorted queries where we will be inserting all the queries. So it will be in the sorted format and it will remove the duplicates. Now I'll be taking the map to remember each of the query count. Okay, so I have taken query count map. I will be taking a min heap, right, and the mn is the size of the entire grid. Now I have taken a visited array initialized to false, which is of size mn as well, and after that I will be trying to apply the BFS. So let's see how to apply BFS. Initially I will be pushing the starting point into the heap and marking it as visited, and since I want to make 4 directional calls, I will be taking the direction vector, and I will be taking a counter which is 0, which will be telling me at any point of time for any query how many nodes have been covered. That means the number of cells covered in the matrix. Then this is the entire BFS that is happening. So for every query we are trying to do BFS. So this code is for the BFS. For every query we are doing BFS. So until the heap is empty, we will be taking out the top of the heap and finding the value XY coordinate from the node and checking if the current value is actually greater than equals to the query. That means you cannot cover this particular cell with the given query. So this node, whatever was taken out, has to be pushed back into the heap, and then we will be breaking this query. That means we are done with this query, right? And once we are done with this query, we will be updating the query count at query equals to count. Okay, so this will be saving the count of number of cells for any query, right? Now if we do not break, and if we actually say that I can cover the cell, then I will be incrementing the count so that I will be noting down that I can cover one extra cell now, and I will be trying all the 4 directional calls. So from the XY coordinate, here XY coordinate, I will be trying all the 4 directional calls in URDL format, URDL, and if the new coordinate is valid and if it is not visited, then I will mark it as visited and push it into the min heap. Okay, and I will repeat this process. So after repeating this process, the query count map will be having the result for each of the queries. So I have to build the answer. So what I'll do is I will be declaring the result array, and I will be parsing through each of the queries in the original order with duplicates, and I will be looking the hash map, the query count map, and for every query I will be getting the count and pushing it into the result, and finally I will be returning the result. So this is the entire code, and I hope it is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of these programming videos. See you guys in the next video. Thank you.